Hello and welcome to this lecture. Today we are starting a new module, and this module is on probability and statistics. In last couple of module we have discussed about different theory related to probability. Basically, those whatever we have discussed is associated with the population. Now, when we talk about the statistics is related to the a few samples taken from this population, or more precisely speaking, it is the some of this random sampling. So the sample that we take, that should be the random sample from the population. So now, as we are using the word the population sample, so at the starting of this lecture, we should know what does this actually mean. And you know that when we are talking about some of these parameters for those distribution that we have seen in the last lectures, in this last modules, that there are certain parameters there which is associated for some standard probability distribution that we have seen. So basically we have to estimate those parameters, and those parameters, when we estimate we should have some sample data, and from there we should estimate those parameters. Now again, the samples means when we are taking the random samples from a population. Now once we change the sample, obviously that that estimation of those parameters may also change, and obviously it will change because two samples will never be exactly identical. So those estimations also will have some distribution. So those are basically called the sampling distribution. And so basically the first lecture that we are going to take in this module is on our this sampling distributions and the parameter estimation. So in this parameter estimation, that what we will do it based on the sum of the sampling distribution. And you know that whenever we talk about the mean or standard deviation or this type of parameters, and which is estimated from the samples, those are also follow some distribution. So we will see what that distribution refers to, and then we can go for its estimation. Now in the estimation theory also, we can do this estimation in terms of two different types. One is that that is the point estimation. The point estimation means just one value I can estimate from whatever the information that is available to me through the random samples. Or what I can do is that I can look for some of this interval of this of the estimation. So that okay, this is the interval, this is the lower limit, this is the upper limit of this particular parameter, so that it will be more logical to say, or in the statistical sense, that instead of giving a single value as the estimate, sometimes it is preferable to give some of this interval. So all these things we will discuss in this lecture. So our outline of today's lecture is that first we will discuss about the population and sample, then the random sampling and the point estimation. As I was mentioning, just a single value we will just pick up, we will just estimate from the sample. Then properties of this point estimation, and there are two methods for this estimation. One is that called method of moments, another one is method of maximum likelihood. And then the interval estimation of this mean, and then interval estimation of the variance, and then estimation of the proportion. So all these things will go. Basically this is this outline should not be a dead end here, so it should continue, and we should have this hypothesis testing also, because these are all very well related to whatever we are going to discuss. So maybe one after another we will take all these topics to discuss about our the statistics which is related to, and each and every point whatever we will be discussing, we will see that where these things are useful to handle the some of the civil engineering problems. So that we will see. So to start with, we will start that about the concept of this population and sample. So the population is the complete set of all values representing a particular random process. So is when we talk about this all values which represents a particular random process, that means this all is very I should say that is a including of whatever the possible range is there, that should include everything. So what I can give the example is that the stream flow in a certain stream over the infinite timeline. So if we are collecting the time series of the stream flow values, so there should not be a finite time over which we are looking the data. So it should be on this infinite timeline. So whatever has happened, what is going to happen, everything. So that is what is our population is. And when we talk about a sample, that sample is any subset of the entire population, and its corresponding example for the stream flow that we have used here is the stream flow in the stream over the last 30 years. So if I just take over the last 30 years, then that particular data set that is available to us is the sample of this population. Now you can see that whatever the probability theory that we have discussed earlier is basically related to its entire possible values, that is all possible values of the random process. But in reality we never get we never have this entire whatever the all possible values that is possible, that we may not have. So we have to rely on some sample, and somehow we have to relate whatever we can estimate from the sample, and we have to relate it to its population. So this is basically the role of the statistics, and with this we will just see how we can estimate the required information from the sample, and then we will infer something about its population. Because as I told that having the entire population is not possible in almost for all the cases. So now in sample, I was mentioning that the random sample, when should we call that a sample is a random sample? So as it is impractical or uneconomical to observe the entire population that I was mentioning, so a sample, that is a subset, is selected from the population for analysis. A sample is said to be random sample when these two conditions are satisfied. One is that it is the representative of the population. Now this word is important, that is it should be the representative of the population. So whatever the possible cases that we can see in the population, the sample should have that representation in it. And second one is that when the probability theory can be applied to it to infer the results that pertains to the entire population. So the probability theory, as I was telling, it is basically relates to the population. Now if we can apply the probability theory to the sample to infer the results that pertains to the population, then we can say that whatever the sample we are taking, that is the random sample. So these are just the concept, and with this concept what we can do is that we can use the whatever we have seen from the probability theory, we can apply to the to this random samples. Now the random sample for finite and infinite population. So you know that there are certain cases where the population can be finite, or in other cases it can be infinite, or sometimes it can be countably infinite, even though I know that obviously there is some maximum number is there, but we can also say that that is countably infinite. So in such cases, what should be the random sample? So first we will take the case of this finite population. An observation set x1, x2, x3 up to xn is selected from a finite population of size n, so that entire size of the population is n, is said to be a random sample if its values are such that each xi of n has the same probability of being selected. Now so as we can see that there is this the size of this population is finite, that is his maximum number is n. So this x1, x2, x3, so we can say that it is a random sample if each of these item have the each of this element of this set have the equal probability of being selected from the population. And second one, if the population is infinite, an observation set again that x1, x2, x3, xn is selected from an infinite population fx. So obviously when we talk about this infinite series, we generally denote it through its probability density function. Here it is that fx is said to be a random sample if its values are such that each xi of n have the same distribution fx and the n random variables are independent. So each observation, now the first observation, second observation, third up to n, these are also, we can say that these are also a random variable. So these variables should have the same distribution which is fx and which is same to the distribution of the population, and all these n elements of the set are independent to each other. Then we can say that this set is one random sample. The classical approach to estimation of this parameter. So the classical approach of estimation of this of the distribution parameter is of two types. One is the point estimation and other one is the interval estimation. So this point estimation means a single parameter value is estimated from the observed data set, that is from the sample. So from the sample a single parameter value is estimated. Now we'll discuss how to estimate that parameter, that we will see. So but here I want to trace the word single. So when the single parameter is estimated, that is known as the point estimation. On the other hand, it will be interval estimation when a certain interval is determined from the observed data set. It can be said with a definite confidence level that the parameter value will lie within that interval. So there are now might be many new things here. One is that it is the interval. So this word, the certain interval, when we are predicting, then it is the interval estimation. Now when we say that this is the interval estimation, then certain confidence level comes. So that with this much confidence, or with this much confidence, and this confidence are also in this in the statistical sense. So sometimes the general values that we use for this confidence levels are the 90% confidence, 95% confidence, 99% confidence. So this confidence level can vary from the 0 to 1 basically. So means 0% to 100%. So whenever we say that it is an interval estimate, these interval estimations are always associated with some confidence level, and we will see all these things how we can declare that this is the confidence for this interval. But one thing is should be clear here now is that this confidence level, if I increase the confidence level, so that means, as you can read from this sentence, that it can be said with a definite confidence level that the parameter value will lie within that interval. Now suppose that I take two cases, one is that 95% confidence level, other one is the 99% confidence level. Then obviously the 99% confidence level is more, so that the chance of the exact parameter value will lie within that interval in case of the 99% confidence should be more. So obviously the interval estimate that we are doing should be more wider in case of 99% confidence in interval compared to what we can estimate in case of the 95% confidence interval. So more the confidence level, wider is the interval. So that is what we can see at least at this stage. We will discuss all these things. Now the random sampling and point estimation. So first we will take that point estimation out of these two estimates. As the parameters of the distribution of a population are unknown and it is not feasible to obtain them by studying the entire population, hence a random sample is generally selected. The parameters of the distribution that are computed based on the analysis of sample values are called the estimator of the parameters. So whatever the quantity that we try to estimate as the estimate of that parameter is known as the estimator. So there are two things, one is estimation, another is the estimator. So through what through what function, I can say, through what function I am trying to estimate that parameter, that is known as the estimator. Thus parameters correspond to the population, while estimators corresponds to the sample. So that this is what, so when we are talking about the parameters of a distribution of a particular probability distribution, say, so that is generally corresponds to the population, and when we talk about the estimator, that is correspond to the sample. So if we take the example of this normal distribution that you have seen earlier, is that there are two parameters now, one is the mu and other one is the sigma square. Mu is the mean and the sigma square is the variance. So that mu and sigma square, these are the properties, these are related, these are associated with the population. Now how we will estimate that mean, that is mu, and how we will estimate that variance from a sample? So those are the estimator and those are associated with the sample, that we will see now. So when we say that there is a point estimator, and that point estimator is, that should have some properties, and these properties, there are 4 different properties that a point estimator should have before we can use that one, because you see that there could be the many functions that we can use to estimate that particular parameter, but so we have to take that particular function which is satisfying all these properties, or at least the more maximum number of these properties should be satisfied by those estimators. So these 4 properties are the unbiasedness, consistency, efficiency and sufficiency. So we will take one by one. The unbiasedness is that bias of an estimator is equal to the difference between the estimator's expected value and its true value. For an unbiased estimator of the parameter, expected value should be equal to the true value. Now when we are talking about this true value, that means it is the value for the population, that is mu. Now whatever the estimator, from the estimator which is we are getting which we should for which we should use the sample that is available with us, and as I have told that these estimators also have some distribution. So as these estimators are also having some distribution, so we can also calculate whatever the properties that we knew from our earlier lectures and modules, is that, so one is that the expected value. So if I take the expectation of that estimator itself, so that will reach to one value. Now the difference between this expected value of the estimator and its true value should, so obviously the desirable thing is that it should be as minimum as possible. So and that is the bias. So the estimator should be unbiased, and this is the property that is written here. At least when we see that if the n tends to infinity, means the n, when the n is the number of sample that we take, so when the n tends to infinity, then if that expectation of the estimator should be equal to its the population parameter. So if that is the case, that is basically the check for this unbiasedness. Second is the consistency. It refers to the asymptotic property whereby the error in the estimator decreases with the increase in the sample size of n. Thus as n tends to infinity, estimated value approaches to the true value of the parameter. So this is the consistency, that is, as we are increasing the number of element in the sample, the estimator should be such that the value of the estimator should approach to the true value of the parameter, that is the parameter of the population. Third one is the efficiency. An estimator with lesser variance is said to be more efficient compared to that with a greater variance, keeping other conditions same. So here you can see that suppose we got 2 estimator and both the estimators can satisfy the first 2 properties. One is that both are unbiased and both are what is called the that consistent. So if both are satisfying the first condition, then we have to select the estimator which is having the less amount of the variance. So this is basically a relative thing, which one is more efficient estimator. The estimator having the lesser variance is more efficient in such cases. And sufficiency, if a point estimator utilizes all the information that is available from the random sample, then it is called a sufficient estimator. Now we will discuss this thing through there are two commonly used method of this point estimator, and this will apply to one of the known distribution and can easily be handled through the this hand calculation problem that we will see. So the two commonly used method for this point estimation is the point estimation of the parameter are the method of moments, and other one is method of maximum likelihood. So first we will take this method of moments. The method of moment is based on the fact that the moment of a random variable have some relationship with the parameters of the distribution. So whatever the sample that we are having, we will calculate what are the moments of that random variable, and that should have some relationship with the parameter of the distribution. And we have discussed this thing, the first moment, second moment with respect to the origin. You know, the first moment with respect to the origin is the mean, and second moment with respect to the origin we generally we can take, but we generally don't take. From the second moment onwards, we take it with respect to the mean, and that gives the expression for the spread of the distribution. All these things we have discussed earlier, and we have also discussed that the first moment with respect to the mean is 0. So that concept we have discussed earlier. So here we will use that concept to use in this method of moments. So if a probability distribution has m number of parameters, then the first m moments of the distribution are equated to the first m sample moments, resulting m number of equations can then be solved to determine the m number of parameters. We will take two examples. One is that say for example that exponential distribution. So exponential distribution is having one parameter that we know, the lambda. One parameter is having, so the first moment of the sample that we are having should be equated to the first sample moment. Whatever the sample that we are having, we can also calculate what is its first moment with respect to origin, of course, and that we can equate to get that what is the estimate for this lambda. We take another example, that is say that normal distribution or gamma distribution, both are having two parameters. So for normal it is mu and sigma square, and for gamma you know that it is alpha and beta. So the two parameters are there. Then the first two moments, first moment and second moment, should be equated to the first two moments of the sample, and this should be equated to those parameters. That is, first one should be equated to the mean and mu in case of normal distribution, and second one should be equated to the sigma square in case of normal distribution. And so there are two unknowns now, and there are two equations also that we can solve to get what are the estimate of those parameters. Now for a sample size n, the sample mean and sample variance, that what we use as their estimator is that x bar is 1 by n summation of all the sample that we are having, and here the sample size is n as it is mentioned here. So we will sum of all this sample and divide by n, that is basically the arithmetic mean, and this is, we can show that this is the estimator for the sample mean which is satisfying all the properties that we have discussed, that is 4 requirements for this estimator. Now this is a square, which is the sample variance, which is 1 by n summation of xi minus x bar. Again, this x bar is that mean estimated through this equation, and this is square summing up from this I minus I equals to 1 to n. Now this is the point estimator for the variance. Now this one, we can show that if we use this one, this will not be unbiased. Now to make this one unbiased, that is, as I was telling, that if the n tends to infinity, it should reach to the actual value. Then what we have to use? We have to use that 1 by n minus 1. So if we use that n minus 1, so in many textbook you will see that this estimator for this variance is that 1 by n minus 1. So that minus 1 is basically to make the estimator unbiased. And you know that this minus 1 that we are talking about is basically we can say that it's that degrees of freedom. So 1 degree of freedom is lost here. That is why we need to get that n minus 1. Why it is lost is that we are using this mean which is also estimated from the sample itself. So that is why. So 1 degrees of freedom is lost here, and so we have to write that n minus 1. Now somehow, if we know what is the population mean, and if we can replace this x bar with respect to the population mean, that is xi minus mu, that square, and if we use this quantity, then there is no need to make that n minus 1, then that 1 minus n is sufficient. So thus is x bar and s square are the point estimates of the population mean and the population variance. So these are the point estimate for those things which is obtained from the sample, and the parameters of the distribution can be determined from these. So these are the first two that mean the are the estimate for the population mean and population variance. So if needed, other higher order sample moments can also be obtained to calculate all the parameters. So that means that we can go to the skewness with sample estimate of the skewness, we can go to the sample estimate of the kurtosis and all. So now the relation between the parameter of some common distribution and the moments are, say for example, here we are taking that normal distribution first. There are two parameters that you know, one is that mu and other one is the sigma square, are equal to the mean and variance like this. So expectation of the x is equals to mean and the variance is equal to sigma square. So what you can see is that directly we can use whatever the estimate that we have done, that we can put here to get what is this population mean and the population variance. Now in case of the gamma distribution, now the parameters are the alpha and beta that relates to the mean and variance as follows, that you know that expectation of x in case of the gamma distribution is the alpha beta and the variance is alpha beta square. So all these things we have discussed in the earlier modules. You can refer to that those lectures. Here we are just using what we have seen in the earlier modules. So okay, fine. So as to conclude this one is that now you are having basically this you can estimate from this sample, this also you can estimate from the sample. Now if you equate this one with these two parameters, that is what we are saying. So we are having that two unknowns here, alpha and beta, and there are two equations. So these two can be solved to get what is the estimate of this alpha and beta. And here it is straightforward because we are getting this mu is the expectation which is directly should be the equal to this x bar whatever we have seen, and the variance should be that sigma square what we have seen in this slide. Okay, and obviously if you are using this x bar, that's which is also estimated from this sample, this instead of 1 by n it should be n minus 1. Now the second method is that method of maximum likelihood. The method of maximum likelihood can be used to obtain the point estimator of the parameters of a distribution directly. So there are some shortcomings of this method of moments, which we generally suppose that sometimes the estimate that using the method of moments, what we get is that sometimes the solutions are once it is solved, we get that the it is not within the range of these parameters. So sometimes this kind of things are observed. So that is the criticism over the method of moment. So there this method of likelihood has found to be more effective, because here directly the distribution we are using, and we are developing a likelihood function, and that likelihood function is maximized to estimate that that particular parameter. Now you know that how to maximize that likelihood function. First of all, we will see what is the likelihood function, and then we will maximize that one. Now as many parameters are there, so we have to maximize all those parameters, so that we will get those many equation to have to solve them to get those estimate. So suppose that if a sample value of a random variable x with density function fx and the parameter is theta here, are this x1, x2, xn, then the maximum likelihood method is aimed at finding that value of theta which maximizes the likelihood of obtaining the set of observation x1, x2, xn. So what we have to do is that the likelihood of obtaining a particular sample xi is proportional to the function value of the PDF at xi. So, so this xi means from this x1, x2, x3 we have to calculate what is that likelihood function. So the likelihood function for obtaining the set of this observation x1, x2, xn is given by these values of this distribution at each point. That is, what is the value of that function at x1, at x2, at x3 and all, and their multiplication. So this differentiating the likelihood function with respect to theta now and equating it to 0. So this is basically we are maximizing the likelihood function. We are finding where this likelihood function will be maximized. We get the value, that is theta value of that estimate, that is theta hat, we can just say, which is the maximum likelihood estimator of this parameter theta. That is, this one will equate to 0, and then we will get that estimate of that theta hat. The solution can also be obtained by maximizing the logarithm of this likelihood function. So if we take the log also, sometimes it will be more that so far as mathematical calculation is concerned, it may become easier, that we will take the log of this likelihood function and we will differentiate with respect to the parameter. And if there are m numbers of parameters of the distribution, then the likelihood function is like this. So there are theta 1, theta 2 up to theta m, these are the parameters of the distribution, and this is, you know, that is the multiplication sign of this at each sample point xi. And the maximum likelihood estimator are obtained by solving the following simultaneous equations. So we have to take the differentiation with respect to each parameter theta j can vary from 1 to up to m, and we can take this partial derivatives equated to 0. So we will get m equations to solve them to get that estimate of these m parameters. Now we will take one example using both the method that we have seen just now, both that that method of moment and method of maximum likelihood. So and here we have taken that example of this exponential distribution, and you know this exponential distribution. Here the example is on this interval time of this vehicle on a certain stretch of highway is expressed by an exponential distribution, where this ft is equals to 1 by lambda e power minus t by lambda. Now in some places, or even in this lecture also earlier, we might have used some other form, that is lambda e power minus lambda t. So it doesn't matter. So there just parameter is taken that 1 by lambda here. So here also, so the form is not changing, only thing the parameter represented in a different way. So if we use that the other form also, that is lambda e power minus lambda t, then also we can get the same result that we will see now. So and obviously here this t is greater than or equal to 0. Now there are some samples has been taken, that is the time between the successive arrival of the vehicle was observed as 2.2 second, 4 seconds, 7.3 seconds, 11.1 seconds, 6.2 seconds, 3.4 seconds and 8.1 seconds. So this is the sample that we have collected. Now determine the mean interval time, that is lambda, by if I don't even want to mention this, what is this, I just want to estimate what is the parameter lambda for this distribution by two methods. One is the method of moments, another one is the method of maximum likelihood. So first, the method of moment, when we say that we should take the moment with respect to the origin and that we should equate with this mean. So if we take this moment, you know that is the first moment with respect to mean that we have discussed in the earlier classes, is that t multiplied by the distribution and taking this integration over the entire support of this distribution, and here this exponential distribution having the support 0 to infinity. So we will take this integration, and if we solve this one, we can see that this mu is equals to lambda here. So this mu, so the lambda is equals to mu, which is we can obtain from this sample as this x bar, which is estimated for this mean. So this 1 by 7 summation of all this ti, so it is arithmetic mean. So 6.04 second is the estimate for this lambda. Now if we use the other form of this exponential distribution, that is lambda e power minus lambda t, then you can see that this mu will become that 1 by lambda. So there the lambda will be equals to 1 by x bar, and this will be 1 by 6.04 second. So it depends on in what way the parameter is used here. And the other one, that is use of this maximum likelihood function, that is so assuming the random sampling, the likelihood function of the observed value is, that is t1, t2, t3 up to t7. So all this sample will take, and this will get what is the likelihood function first. So 1 by lambda e power, so e power minus ti by lambda. So at all this observation we are getting this value and we are multiplying them with each other. So this lambda power minus 7 exponential of this value will get, and the estimator can now be obtained by differentiating the likelihood function L with respect to the parameter, that is lambda. So if we do that, if we do this derivative we take with respect to the lambda, then we will get this form, and if we just equate it to the 0, then after solving this form you will get that again the lambda is equals to 6.04 second. So for this one, this example that we have shown, for both the method, whatever the parameter that we have estimated are same. For the lambda is equals to 6.04 second for both the methods, that is method of moment and method of maximum likelihood. But sometimes in some problems, in some distribution, these two estimate may not be same. Next we will take that interval estimation. So as I was telling that in this point estimation we generally get a single value, that what we have seen in the previous example also in both the methods, the method of moments or method of maximum likelihood, we get the single value, that is the lambda value that you have seen, that 6.04 seconds. So only a single value that you have seen in the point estimate. Now in the interval estimate we generally look for a interval in which with some confidence that actual value of the parameter should lie. So this is what this interval estimation. So in case of point estimate, the chances are very low that the true value of the parameter will exactly coincide with the estimated value. So as this sample is finite, always there will be some error. So hence sometimes it is desirable or it is useful to specify an interval within which the parameter is expected to lie. The interval is associated with certain confidence level, that is it can be stated with certain degree of confidence that the parameter will lie within that interval. So this is what we are discussing few minutes ago, that always this estimate, whenever we say that this is the interval, so that interval must be associated with some confidence level in statistical sense. Well, so the confidence interval of the mean with known variance. So so whatever the estimator that we have seen for this mean, and as we are taking it from the sample, so that will also have some sampling distribution it should have. And if we somehow know what is the variance, the known variance means we know the population variance. If we know that one, then how we can get that confidence interval for the mean. So for a large sample n, so large sample is again this is a subjective word. So generally we have seen that if n is greater than or equal to 30, then we can say that in case of mean only, so not for all in general case. In case of mean, if the sample size is greater than 30, then we can say that it is a large sample. So in such case, if x bar is calculated a sample mean, and this sigma square is the known variance of the population. So sigma square I know which is the actual value of this population. How we know, that is the second issue, but we know this sample population, we know the variance of the population. Only thing we are interested to know what is the interval for this sample mean. Then it can be shown that this x bar is a normal distribution with mean equals to mu, which is the population mean, and the variance of this x bar, that is this sample mean, variance of the x bar is sigma square by n, or the standard deviation of this x bar is sigma by square root n. So this what I want to repeat once again, that this sigma square is the variance of the population for the random variable x. Now what we are talking about is this x bar. This x bar is again another random variable which is normally distributed, having the same mean of the population, which is mu, and its standard deviation is sigma by square root n. Now you know from the from our earlier lecture that this, if we just take this quantity now, that this what is the random variable minus its mean divided by its standard deviation is a standard normal distribution. So that is why this x bar minus mu by sigma square root n is a standard normal variate. So now for once we know that this is the quantity and this follows the standard normal distribution, now we can calculate whatever the confidence interval that we are looking for. So the confidence interval of the mean mu is given by is this, that is x bar. Basically we are just equating it with two side of the standard normal distribution. Now if you see this one here, so if this is your standard normal distribution, then basically that quantity, that is x bar minus mu by sigma by square root n, that should, so this is the standard normal distribution. So this, the distribution that I have drawn is the standard normal distribution. So this should lie between these two values here, so in such a way that this area should be your, that whatever the confidence limit that you wish to specify. Okay. Now so this is the confidence level of that estimator that it should have. Now if I just say that this this confidence level is at some level, say that 95% confidence level, so whatever is remaining here is your 0.025, and whatever is remaining here is again 0.025. So we have to find out these two values. Suppose that if I just put that one z alpha by 2 and this is, say that z alpha by 2, obviously this will be the negative side, this is 0 for the standard one. So this one, so this quantity should lie between this z alpha by 2 and this z alpha by 2, where this alpha by 2 are basically the cumulative probability up to that point. Okay. So so this x bar minus mu divided by sigma by square root n should lie between these two, z alpha by 2 and this minus z alpha by, sorry, z alpha by 2. So z is the variate, is the reduced variate for the standard normal distribution, and this alpha by 2 is this part where we are. So, the confidence, if I just want to relate to this confidence level, is that it will be that 1 minus alpha multiplied by 100 confidence level. So, this is the confidence level that we can say. So, that if this area, this white area is the alpha by 2, then this 95 that is here in case of 0.25 here can be related to this one. So, this is that confidence interval that we are that is the confidence level that we are talking about for this. Once we can put these limits as this z alpha by 2. Now, if I just do some arithmetic change, then it will come like this, that is mu should be equals to here that x bar plus z alpha by 2 sigma by square root n, and here it will be x bar minus z alpha by 2 sigma by square root n. So, you remember that even this alpha by 2 when we are talking about, so so this alpha by 2, it is automatically when it is coming to this negative side, it have this negative value. So don't confuse that this will have this have the negative value and this again another negative sign is here. So, it will not be the plus. So, this is a single value that we are using here, which should have that this particular quantity. From the symmetry, both the values will be same numerically, only this one will be positive and this one will be negative. So, this is what is mentioned here, that is x bar minus z alpha by 2 sigma by square root n minus mu less than x bar plus z alpha by 2 sigma by square root n. So, you know that from the continuous distribution less than and less than equals to are same, where this 1 minus alpha into 100%, this is the quantity which is the degree of confidence, and here this minus plus z alpha by 2 is the value of the standard normal variate at the cumulative probability level alpha by 2 and 1 minus alpha by 2. So, when you are taking this minus sign, minus z alpha by 2, this is the probability level at this alpha by 2. So, if it is 95, if you put this alpha equals to 0.95, then obviously 1 minus sorry, this is full is equals to 0.95, then alpha will become 0.05 and this alpha by 2 will become 0.025. Now, at this 0.025, this z alpha by 2 will be, say if it is 0.95, you know that this value will be 1.96. So, this will be x bar minus 1.96 multiplied by sigma by square root n, and here also plus 1.96 sigma by square root n, this will come. Now, as we are discussing that if the sample is more, if the sample is large, if it is more than 30. Now, in other case, if the sample size is small, say if it is less than 30, and if the x bar is the calculated sample mean and this then this s square is this calculated sample variance, then the random variable x bar minus mu divided by s square root of n follow a t distribution with n minus 1 degrees of freedom. Here you see this is that the variance we do not know, that is the unknown variance. So, this one also we have to calculate from the sample itself. So, this also again when we take that this x bar minus this population mean divided by this sample variance divided by square root n. So, this one instead of following this standard normal distribution, it will follow the t distribution with n minus 1 degrees of freedom. So, this t distribution and all we have discussed earlier. Only thing is that if the sample size is small, this quantity will follow the t distribution. If the sample size is more and this variance is known, then this will follow a normal distribution. So, here in this case, this confidence interval will be x bar minus t alpha by 2 sigma by square root n and x bar plus t alpha by 2 sigma by square root n. So, this is the t distribution with degrees of freedom n minus 1, and you can see even that from standard textbook about this t distribution, when this n goes beyond 30, then the value of this t alpha by 2 and the z alpha by 2 are essentially same. where this again that 1 minus alpha into 100% is the degree of confidence, and minus t alpha by 2 is the value of the standard t distribution variate at cumulative probability, again that alpha by 2, and this 1 minus alpha by 2. So basically the difference between the t and the standard normal distribution is at this lower n level, where you will get a wider estimate of the interval, because when the sample size is less, as well uncertainty is more. Though it is assumed that the sample is drawn from a normal population, the expression applies roughly for non-normal population also. So basically when the population is normal distributed, these are very well acceptable method, but even though it is non-normal also, this method we can apply. So we will take one example of this. Whatever we have seen is that 30 concrete cubes prepared under certain condition. The sample mean of these cubes is found to be 24 kilonewton per meter cube. If the standard deviation is known to be 4 kilonewton per meter cube, determine the 99% and 95% confidence interval of the mean strength of the concrete cube. So this 4 kilonewton per meter cube is known, it is from the population, and this one when we say that this one is obtained from this sample. Okay. So if we want to solve this one, then you know that we first of all we will get that what should be the quantile value for this z alpha by 2, and this is for this 99% confidence interval from the standard normal table. You can see that it is 2.575, which is z alpha by 2 value. So this sigma by square root n multiplied by z alpha by 2 is equals to 1.88, whatever the data is available. So the 99% confidence interval will be the mean minus that quantity 1.88 and mean plus 1.88. So this confidence interval is 22.12 and 25.88 kilonewton per meter square. Sorry. To determine the 95% confidence interval, again we have to find out the z alpha by 2, and this is your 1.96. Earlier it was 2.575, so it is now 1.96. So if we calculate this one, it will become 1.43, and the 95% confidence interval of the mean strength of this concrete will be 24 minus 1.43 and 24 plus 1.43. So 22.57 and 25.43 kilonewton per meter square. Sorry, this is, or this is the density. Sorry, this is the density. So it is kilonewton per meter cube only. But what we should observe here is that there are two confidence interval we have determined. One is the 99% confidence interval, and the other one is the 95% confidence interval. So the 95% confidence interval is 22.57 to 25.43, whereas the 99% confidence interval is 22.12 and 25.88. So you can see that this 99% confidence interval is wider, because it is more likely that the larger interval will contain the mean value than the smaller one. So hence the 99% confidence interval is larger when the 95% confidence interval as compared to this 95% confidence interval. So this example that we have used, it is we have taken that variance is known. So once we have decided the variance is known, we have used the standard normal distribution. But in the other case, we have seen that sometimes the sample size is less, and we have to use, in that case we have to use that what is the t distribution. From the t distribution table we have to use that one. So maybe we will take up the same example, but in that time we will just declare that whatever the distribution, whatever the standard deviation that we got, it is not from the population but from the sample. So that example we will basically start from the next lecture, and after that we will take what should be the that estimation for the other parameters like the variance, proportion and all, and we will also relate, we will also see about this test of hypothesis, which is obviously essential when we are comparing the mean of from the two different samples, or the variance or proportion from. So when it is related to two different sample, then we have to go for those testing. So we will start from this point in the next lecture. Thank you.